We measure the progress of human history through the earth we extract. Over 3 million years, the capacity to project power has relied on the mastery of physical matter, taking raw stone, forging it into metal, and etching it into silicon. You were likely taught a rigid, linear progression of this mastery, a march from the Stone Age into the Bronze Age, and finally the Iron Age. But this sequence is a regional heuristic. It was built to help archaeologists organize local evidence, not to describe a synchronized global reality. This chart maps the timeline of global adoption, and the chronological boundaries immediately overlap. China, for example, adopted iron smelting centuries later than the Near East. Across parts of sub-Saharan Africa, societies transitioned directly to iron metallurgy without ever having a distinct Bronze Age. We see similar anomalies in East Asia, where foraging societies developed ceramics roughly 20,000 years ago, thousands of years before the invention of agriculture. Pottery did not strictly require farming. Historical epochs track a society's mastery over the physical properties and supply chains of dominant materials. To understand how any empire organizes its military and political capacity, you have to map the geographic distribution of its critical technology. History is a spatial map of resource constraints. Those physical limits mechanically dictate the rise, the reach, and the inevitable collapse of human networks. Roughly 12,000 years ago, the erratic temperatures of the Pleistocene gave way to the Holocene, bringing a relatively stable, warming climate to the globe. This map tracks the resulting Neolithic revolution. It was a polycentric phenomenon. Agriculture emerged independently across unconnected nodes, from the Fertile Crescent to the Yangtze River Valley to Mesoamerica. Archaeological evidence reveals a surprising sequence. The gathering of massive labor forces for monumental ritual construction actually preceded full-scale farming in several regions. We see the physical proof of this in southern Turkey. These T-shaped limestone pillars were erected 11,500 years ago, requiring massive coordinated labor long before the adoption of agricultural economies. Once grain agriculture fully took hold, the resulting caloric surplus enabled extreme demographic density. Settlements like Çatalhöyük supported thousands of inhabitants, living in tightly packed, contiguous mud brick structures. Yet, while the systematic cultivation of wheat and barley generated the calories necessary to sustain these populations, these societies remained geographically confined. The Neolithic package created local demographic hubs. Without monopolizable, durable materials to equip a military force, these early societies lacked the mechanical capacity to project imperial power beyond their immediate river valleys. The barrier to projecting power was broken by a metallurgical innovation, alloying copper with tin to create bronze, producing weapons far superior to stone. This map plots the strict geological constraint of this new material. Copper deposits were scattered across the Mediterranean and Near East. Tin, however, was exceptionally rare, found only in distant, isolated locations. Combining them required empires to forge vast, long-distance trade routes. The reality of this supply chain is perfectly preserved in the cargo manifest of the Uluburun shipwreck, which sank 3,300 years ago carrying copper from Cyprus alongside tin from Afghanistan. Managing a supply chain spanning thousands of miles required immense capital and coordination. It forced the creation of centralized political structures to fund and protect the flow of metal. This bottleneck birthed the palace economy. Elite merchant classes and sovereign authorities merged, existing primarily to control the acquisition and distribution of bronze. To maintain control over these assets, centralized states developed the world's first complex diplomatic bureaucracies and writing systems, originally designed to track inventory and tax yields. Administrators relied on dense, grid-like script. Cuneiform tablets allowed the state to strictly account for every ingot of metal moving through the network. This Bronze Age system was highly optimized for resource extraction, but its reliance on distant, interconnected nodes made it incredibly fragile. In the 12th century BCE, a convergence of climate megadroughts, earthquakes, and internal rebellions severed these delicate trade routes. The polis economies were starved of their critical alloy. The collapse of the Bronze Age demonstrates a mechanical systems failure. The destruction of these empires was caused by an over-reliance on a geographically fragile material network. As the Bronze Age network shattered, societies were forced to turn to iron. Iron offered a distinct advantage. Its ores were geologically ubiquitous. This gauge measures the technical barrier delaying its adoption. Copper melts at a lower threshold, but smelting iron requires sustaining a massive thermal jump to 1250 degrees Celsius. Mastering this threshold provided access to a metal distributed in massive abundance across the Earth's crust. The mechanical effect was immediate. States no longer had to rely on fragile, long-distance trade routes to equip their forces. Cheap, locally sourced iron democratized the capacity for violence. The military economics shifted from small units of elite aristocratic charioteers to massive armies of conscript infantry. By lowering the cost of arming a soldier, iron fueled relentless, large-scale warfare, mass population migrations, and aggressive territorial expansion. This capacity for mass warfare enabled the rise of classical territorial empires. The massive geographic scale of Han China and the Roman Empire was built directly on the logistics of iron. That mass mobilization of resources and labor extended beyond the battlefield, allowing these empires to construct the enduring, monolithic civic structures that defined their authority. The transition to the Iron Age proves a distinct mechanical rule. True continental hegemony is achieved not by controlling a rare resource, but by mastering the physics of an abundant one. Over the millennia, the raw materials of power evolved. We transitioned from the physical force of forged metal to the invisible architecture of digital processing. The Industrial Revolution shifted the limiting constraint of civilization. Power moved from the metallurgy of weapons to the management of mechanized fossil fuel energy regimes. This graph tracks the time it took for transformative technologies to spread globally. As energy regimes advanced, we see an exponential shrinking in the adoption curve, moving rapidly from steam power to electricity to the internet. Today, the information age is anchored to a single atomic component, the semiconductor. This is the first transistor. Its crude physical wiring from 1947 is the physical origin point for the global processing power we rely on today. The modern geopolitical map is drawn by this technology. Power is now dictated by the location of semiconductor fabrication plants, hyperscale data centers, and the extraction of critical clean energy minerals. We have built a highly optimized, interconnected global network. Its structure closely mirrors the fragile, centralized supply chains of the late Bronze Age. While our materials have changed to silicon and agentic artificial intelligence, our global systems display the exact same compounding vulnerabilities: global pandemics, regional wars, and highly concentrated supply chain choke points. Civilizational endurance requires political institutions that can adapt to the specific physical constraints and fragile supply chains of their dominant technologies.